And welcome back to AWS Julie. Let's continue our new playlist where we are talking about the machine learning fundamentals that you need to understand to help you prepare for the AWS Certified Machine Learning Engineer Associate Certification Exam. We finished Domain 2 in the last video, so let's get started with Domain 3, which covers deployment and orchestration of your machine learning workflows. So in the last few lessons, we talked about the first 4 steps in the machine learning engineer lifecycle: to collect data, to process data, select our algorithm, and to train the model. So this domain, Domain 3, covers the 5th step of the machine learning lifecycle, which is to host the model. And for the well-architected machine learning lifecycle, this is step 5, which is deployment. The first task from the exam guide for Domain 3 is select deployment infrastructure based on existing architecture and requirements. Before we begin, let's step back to the fundamentals and talk about the 5th step of the machine learning lifecycle, which is to host our model. A machine learning framework is a way to abstract away complexities that you would have to deal with in low-level code. So what are some examples of machine learning frameworks? Well, there is scikit-learn, MXNext, PyTorch, and TensorFlow. And in machine learning, there's a lot of low-level code, especially for neural networks, but also in linear regression. There are many dimensions to the data, and it gets more complicated, and you need to have more efficient code. And developers spend time optimizing their code and dealing with the low level, the mathematics and equations. And for the exam, you don't need to understand all of that at a deep level. These frameworks do the heavy lifting of putting the code together and providing a library to get you going. You do not have to code anything yourself. You can just use the frameworks to build your machine learning solutions. Let's also talk about other frameworks that are listed as machine learning frameworks, but they're not really. So Keras is actually a layer that exists on top of a framework that extracts you away even further from the framework. Keras can be used on different frameworks, but it is usually used on top of TensorFlow. If you're using TensorFlow for your neural network or convolutional neural network, and you want to train your data set for a problem that has already been solved, then you can use Keras to have your own version and train your own model. And Keras abstracts you away from that complexity of TensorFlow, and you can dive into training your data set. Gluon is a framework that sits on top of MXNext and gives you the ability to abstract away the complexity of the MXNext library. So basically, frameworks help to make machine learning easier for us to solve our problems. I want to dive a bit deeper into hosting and inference before we get into the specifics of hosting in AWS and talk about different methods for hosting and inference. And let's jump back to our machine learning lifecycle. We collect the data, we process the data, we select the algorithm, we train the model, we host the model, and then we make inferences. The model is a combination of the machine learning frameworks, configurations, and binary data, and you have an executable that you can do something, host the machine learning model, and make that inference. For example, that inference can make predictions with new data, and we are getting an answer to the question with a piece of data that the model has not seen before. So you have a computer program, which is the model, and you can give this model inputs and get outputs. But there are different ways to do this. The first method is to do batch inference. Batch inference has pre-existing data, and you want to make inferences on the data inside of the batch. And with batch inference, there is not a hosted model. This batch data is stored somewhere and is not running inside a model yet. So with batch inference, you must first create a running instance of the model and then send the data to the model. The model runs through the data in the data set, performs inference, applies labels, and so on. And then once that's complete, you can delete your model. Batch inference is for data that you already have, and it can be achieved at a lower cost. And you can get a lower cost by using spot instances. Use cases and scenarios for batch inference might be data analytics, time-based data, and recommendation engines. Then there is also real-time inference that has a model that is already running. You pass the data in and you get the inference out. And a big difference between batch inference and real-time inference is that batch data you already have and it's saved somewhere. Real-time inference is used with data that you have not yet received. Real-time inference does have a higher cost because the model is up and running. It is consumer-driven because it answers questions when asked in real time. And use cases and scenarios for real-time inference are chatbots. Let's continue on with task statement 3.1, which is to select deployment infrastructure based on existing architecture and requirements. And again, let's step back to the AWS machine learning stack, which we've talked about a few times so far throughout this course. On the bottom of the stack, there is the infrastructure and machine learning frameworks, such as Amazon EC2 instances, Amazon machine images, GPUs, containers, and more. Everything is built on top of this infrastructure layer. And remember, for your workloads in AWS, you can choose from 3 different levels of machine learning services. You have machine learning frameworks and infrastructure, machine learning services, and artificial intelligence services that you can use for different use cases. Here's a question that we already talked about in an earlier lesson. What makes Amazon SageMaker different from other AWS services? Well, first, the Boto 3 Python library can configure SageMaker, and it has its own dedicated SDK for Python. Also, SageMaker has data labeling services, tools such as SageMaker notebooks, containers, pre-written document samples, algorithms, and examples of those algorithms that are already in SageMaker, and infrastructure management and capabilities. There are also tools under the machine learning operations or ML ops. Part of this task statement and the next one too is understanding how you deploy your machine learning workflows with containers. In an earlier lesson, we talked about how Amazon SageMaker has Docker containers. Remember that SageMaker uses containers differently from Amazon Container Service or Amazon ECS or Amazon Kubernetes Service or Amazon EKS. SageMaker does not use containers to scale, but instead as a method to deploy code binaries in the environment to Amazon EC2 instances running inside AWS. So for the infrastructure layer, for the infrastructure level, there is an infrastructure layer, and we've talked about this earlier as well. But on top of that infrastructure is a Docker container infrastructure. And remember that these containers are run to support machine learning workloads. And you can use your own containers or containers created by AWS. And these have the built-in algorithms. These built-in algorithms are real algorithms created by scientists, and AWS takes these existing algorithms and creates versions of those in SageMaker. And then SageMaker takes the algorithms and containers in SageMaker and manages all of the orchestration. You can also use SageMaker to train algorithms, and the way that works is that it will deploy a Docker container to run a training job. And then you can run hyperparameter tuning jobs, which is a batch way to run multiple training jobs, and monitor the performance metrics and tuning the jobs and tweaking your hyperparameters as much as it can for you. SageMaker can also perform inference and host models and create endpoints. Amazon SageMaker Inference Recommender is a capability of SageMaker that reduces the time required to get machine learning models in production by automating load testing and model tuning across SageMaker machine learning instances. You can use Inference Recommender to deploy your model to a real-time or serverless inference endpoint that delivers the best performance at the lowest cost. Let's continue on with task 3.1. to select deployment infrastructure based on existing architecture and requirements, and let's cover a few questions on SageMaker hosting services. After you train your machine learning model, you can deploy your model using SageMaker to get predictions. What SageMaker hosting service do you use if you need persistent, real-time endpoints that make one prediction at a time? SageMaker real-time hosting services and real-time inferences. What if you have workloads that have idle periods between traffic spurts and can tolerate cold starts? What would you use? Serverless inference? And what if your requests have large payload sizes up to 1 GB, long processing times, and near real-time latency requirements? What would you use? Amazon SageMaker asynchronous inference. SageMaker also provides features to manage resources and optimize inference performance when deploying machine learning models. SageMaker Neo is a capability of SageMaker to train your model once and then run the model anywhere in the cloud and at the edge. Neo is tested with computer vision models available in the model zoos across the frameworks. SageMaker Neo supports compilation and deployment for two main platforms, cloud instances and edge devices. Let's quickly cover compute and start with fundamentals and talk about the differences between training and inference. As you build your compute architectures for machine learning, it is important to understand whether you're dealing with training or inference. If you're doing computer calculations or recognition of imagery, you will need a lot of compute power to train the models because of the hundreds, thousands, or billions of calculations that are needed. And the processing of these calculations will require compute processing units or CPUs that are fast, flexible, and perform consecutive operations. You will also need graphic processing units or GPUs that are fast and focused in floating point operations and concurrent operations with the multiple cores that are inside the GPU cards. For example, neural networks commonly use GPUs, but it is important to make sure the frameworks support the GPUs or code that you are using. I also want to mention tensor processing units or TPUs. It is a GPU that is specifically architected to work for machine learning. I kind of like to think of it as a super-powered, multi-dimensional array used inside of deep learning machine learning problems, and it's where the TensorFlow's name comes from. But to complete inference for those models, you do need a lot of compute power, and this ties into scaling. So let's talk about some of the aspects of training machine learning models and compute. Ensure you understand how you can use multiple cores and how you can distribute your code among those multiple cores. We talked about this under hyperparameters. You may need to increase the mini batch size to make use of the available cores. Also, sometimes in machine learning, we need to scale vertically and increase the compute size, which increases the number of cores. But horizontal scaling is usually best because you get more machines, but you need to ensure that the code, the framework, and the algorithm must support that parallel training and running on multiple parallel machines. And this reduces the time to train, but remember that each machine will train a mini batch, and then they get split between the different machines and different cores. And you may also need to increase the learning rate if you increase the mini batch size. Let's talk about Amazon ECR, which is a managed service for processing large-scale data using distributed compute. It supports Apache Spark, Apache Hadoop, Apache HBase, and Presto, which are all open source projects that deal with distributed processing and MapReduce type operations. MapReduce splits up data across multiple nodes in a cluster, then splits up the jobs across multiple nodes in the cluster. And you can build and deploy these distributed environments on Amazon EC2 instances and Amazon EKS. Core nodes have storage, HDFS attached, but task nodes do not have that storage. And you can use EMR Studio notebooks, which are a managed Jupyter notebook that you can use as an IDE into the EMR environment to manage the code, such as Scala, R, Python, and SQL that runs inside of your EMR cluster. Apache Spark is an open source tool that works in the EMR environment, and it is fast because it runs completely in memory. You can run Apache Spark with Python, Scala, or SQL, and you can analyze the data inside EMR from this in-memory perspective. And Amazon EMR with Spark has capabilities for machine learning. EMR with Spark has a library of code called Spark MLlib, and MLlib is a library that runs inside of Apache Spark to perform machine learning processes such as building models for classification, regression, decision trees, recommendation, cluster, topic modeling, and you can also do feature transformation, machine learning pipelines, model evaluation, machine learning persistence, and more. You can use MLlib to create models from the algorithms we've talked about in the earlier lessons throughout this course. And then the algorithms are pre-baked into MLlib, and you can use them to train your data that is inside of EMR through Spark. You can use MLlib to not only train the model, but run that model. And with this design, AWS is just supporting the machine learning inside of EMR, but you can also use the SageMaker Spark library. The SageMaker Spark library is a specific SDK for your Spark code to interact with the SageMaker services. It can do things such as call upon the k-means algorithm, the principal component algorithm, or XGBoost, which remember are all pre-built algorithms inside of SageMaker. And you can also extend it out with the estimator model. And if you choose to use SageMaker Spark library instead of MLlib, you will also not need cluster training and hosted production endpoints. And long story short, this means that you do not need to offsize your cluster for the training job you need to complete. And you can host your production endpoints outside of your EMR cluster and have infrastructure spun up to make inference on your model. And this is all outside of your cluster. If you're running your EMR cluster to perform jobs, analyze data, and complete statistical analysis, then you do not want the EMR cluster to also train jobs and host production endpoints. AWS Batch is a fully managed service to manage batch compute jobs in AWS. The jobs are defined inside of containers, and the containers are used for deployments for the executable code and scripts that we want to use to process data. And the components of AWS Batch are the compute environments, job queues for prioritization, and job definitions, which are descriptions of what we want the job to look like. The options for AWS Batch compute environments are Fargate and EC2. If you use Fargate as your compute environment, you need to choose the max vCPUs that you need to have available. If you choose EC2, you can set the maximum, minimum, and or desired vCPUs, and you can also select GPUs. And for both, you can use on-demand instances or spot instances. Job queues are linked to the compute environment, and job queues can have one or more or many compute environments. And you can select the priority order of the environments to use. Each queue has a priority that can be set, so you can finish one job faster and then another queue that has a lower priority. And the job definitions sit inside AWS Batch and are configurations which describe which container you're going to use for a job, such as your vCPU, memory requirements, IAM roles, and more. And if you're using EC2 as your compute environment, you can choose GPUs, and the data is stored in Amazon S3 and is wrapped in a job definition, and that creates a job. That job is passed into the job queues and is processed using the compute environment and then outputs your data. And this is lots of data since it is batch data. We know that SageMaker provides infrastructure and model deployment options to help meet all of our machine learning inference needs. We know it is a fully managed service and integrates with MLOps tools to help us scale our model deployments, reduce inference costs, manage models more effectively in production, and reduce our operational burden. After you've built and trained a machine learning model, you can use SageMaker Inference to start getting predictions or inferences from your model, and you can either set up an endpoint that returns inferences or run batch inferences from your model. If you have multiple models that use different frameworks and require their own containers, then you can host multiple models which use different containers behind one endpoint. With this option, you get many of the benefits of multi-model endpoints, and you can deploy a variety of frameworks and models too. If you want to host models with pre-processing and post-processing logic behind an endpoint, then use serial inference pipelines. Inference pipelines are fully managed by SageMaker and provide lower latency because of all of the containers are hosted on the same Amazon EC2 instances. You can also use an existing Docker container in SageMaker or create a new Docker container and receive guidance on how to run your own inference code. After you have an endpoint and understand the general inference flow, you can use features of SageMaker Inference to improve your inference workflow, such as monitoring, and we'll cover monitoring and model monitor under Domain 4. Other features of SageMaker Inference are SageMaker MLOps to automate the steps in our machine learning workflow and practice CI/CD. And SageMaker also supports using your own third-party Git repo for creating a CI/CD system. For your machine learning pipelines, you can use Model Registry to manage your model versions and the deployment and automation of your models. If you want to update your model while it's in production without impacting production, you can use deployment guardrails. Deployment guardrails are a set of model deployment options in SageMaker Inference to update your machine learning models in production. Using the fully managed deployment options, you can control the switch from current model in production to a new one. Traffic shifting models give you granular control over the traffic shifting process, and built-in safeguards like auto rollbacks help you catch your issues early on. If you need to run large-scale machine learning and deep learning applications for use cases such as image or speech recognition, natural language processing, personalization, forecasting, or fraud detection, you can use Inf1 instances with a real-time endpoint. Inf1 instances are built to support machine learning inference applications and feature the AWS infrastructure chips. Inf1 instances provide higher throughput and lower cost per inference than GP-based units. You can then deploy on Inf1 instances, compile your model with SageMaker Neo, and choose an Inf1 instance for your deployment option. SageMaker provides features to manage resources and optimize inference performance when deploying machine learning models. You can use SageMaker's built-in algorithms and pre-built models, as well as pre-built Docker images, which are developed for machine learning. So that wraps up task 3.1. Let's continue on and talk about task 3.2, which is to create and script infrastructure based on existing architecture and requirements. Let's get started and talk about how to best apply best practices to ensure your machine learning model is maintainable, scalable, and cost-efficient machine learning solutions. Let's start with scalability. So I just mentioned that SageMaker does not use containers to scale. So how does it scale? With SageMaker, you can choose when to autoscale and how many instances to provision or remove to achieve the right availability and cost trade-off for your applications. SageMaker supports 3 autoscaling options. The first is target tracking. You need to select a value of an Amazon CloudWatch metric of your choice, such as the average CPU utilization or throughput, that you want to achieve as a target, and SageMaker will automatically scale in or out the number of instances to achieve that target metric. The second option is to choose step scaling. You create and manage the CloudWatch alarms that initiate the scaling process. When an alarm is breached, Amazon EC2 autoscaling initiates the scaling policy associated with that alarm. The third option is scheduled scaling, which lets you specify a recurring schedule for scaling your endpoint in and out based on anticipated demand. AWS recommends that you combine these scaling options for better resilience. SageMaker Hosting offers instance types to host your model. We mentioned this just a few minutes ago. Your traffic load may be limited by the hardware you have chosen, so consider other hosting hardware. For example, if you want a system to handle 1,000 requests per second, scale up instead of out. Accelerator instances such as G5 and Inf1 can process higher numbers of requests on a single host. Scaling up and down can provide better resilience for some traffic needs than scaling in and out. In order to scale up and down an existing endpoint, you must create a new production variant and shift that traffic. SageMaker multi-model endpoints support automatic scaling to help you manage replicas of models to ensure models scale based on traffic patterns. If you have unpredictable traffic patterns or don't want to set up scaling policies, you can also use serverless inference for an endpoint where SageMaker manages the auto-scaling for you. During periods of low traffic, SageMaker scales down your endpoint, and if traffic increases, then SageMaker scales your endpoint up. Serverless inference also integrates with AWS Lambda for high availability, built-in fault tolerance, and automatic scaling. Here's a question. You are using Amazon SageMaker endpoint to predict outcomes. You need to ensure that the SageMaker model scales. What is your solution? One solution is to configure auto-scaling on the SageMaker endpoint. When you host a model on SageMaker, you can also configure auto-scaling to adjust the number of instances in response to the actual load. Why would you scale horizontally instead of scaling vertically? Well, using a larger instance size would indeed allow for handling more traffic, but we just mentioned there is a limit to the resources in your larger instance size. The question was not specific, and usually horizontal scaling is best. What about using AWS Inference? Would that be a solution? No, AWS Inference is designed for accelerating inference workloads at a reduced cost. AWS Inference-based instances can offer improved inference performance, but they can have failures due to a surge in load. So again, horizontal scaling would be the best choice answer for that scenario. What about using Amazon SageMaker Neo? Would that work as a solution? Nope, SageMaker Neo can help you to optimize the machine learning model for inference on your instances and edge devices. SageMaker multi-model endpoints fully support automatic scaling, which manages the replicas of models to ensure models scale based on our traffic patterns. Only using resources when those resources are needed ensures cost optimization, but you can also optimize the cost of training your models by using spot instances. And for the exam, ensure you understand how to choose metrics for auto-scaling. What metric would you need to monitor for your models? My first thoughts are model latency, CPU utilization, invocations per instance, and explanations per instance. And we talked about using Amazon CloudWatch to monitor Amazon SageMaker. You can build customized dashboards for your CloudWatch metrics that can display multiple metrics and include text and images. So let's move on and continue talking about how to apply best practices to enable maintainable, scalable, and cost-efficient machine learning solutions. We covered scalability and cost optimization, so let's talk about maintainability and automating the provision of your resources, communications, and security. Using infrastructure as code, you can use CloudFormation templates to specify the definitions and configurations of your infrastructure that you're going to deploy. You can use the AWS Cloud Development Kit or AWS CDK for repeatable deployments too. Then for your data pipelines, you can use continuous integration and continuous delivery to implement, test, and deploy your data pipelines. There's also the AWS Serverless Application Model or AWS SAM to package and deploy serverless data pipelines such as Lambda functions, step functions, and Amazon DynamoDB tables. For version control in CloudFormation, once you have your template definition file, you can commit that file to a source code repository such as S3 or GitHub. Then your CI/CD pipeline can be automated to run when a new version of the file is committed to the source control repository. The goal is to optimize your code to reduce runtime for data ingestion, transformation, training, and more. How would you use CloudFormation to apply requirements for resources in the deployment? You can use CloudFormation to automatically install, configure, and start applications on EC2 instances. This helps to duplicate deployments but also update existing installations without connecting directly to that instance, which can save a lot of time and effort. What is another service? The AWS CDK is also infrastructure as code solution and is an open source framework that builds on the underlying functionality provided by CloudFormation. It helps to define cloud resources using common programming languages and an abstraction model based on reusable components called constructs. The CDK also contains command line tools to create infrastructure as code templates and to initiate, update, and tear down your stacks. You can also use SageMaker Canvas to use machine learning to generate predictions without needing to write any code. Canvas can extract insights from your data for different use cases and is powered by AI services such as Recognition, Text Track, and Comprehend. You can import your data and start using a solution to generate predictions or build your own model for your use case and train your model with that data. You can also bring your own models into Canvas from Amazon SageMaker Studio. Remember, we said earlier that SageMaker provides APIs, SDKs, and a command line interface that you can use to create and manage notebook instances and to train and deploy your model. Let's move on and talk about another best practice, which is ensuring security and secure connections. How do you configure secure connections for your Amazon VPC networks and your SageMaker endpoints? Well, instead of connecting over the internet, you can configure and connect to the SageMaker API or to Amazon SageMaker runtime through an interface endpoint. When you use a VPC interface endpoint, communications between your VPC and the SageMaker API or runtime is within an AWS network, and these connections can be set in your CloudFormation template, which ties back to maintainability and scalability. Each VPC endpoint is represented by one or more Elastic Network interfaces with private IP addresses in your VPC subnets. So if you have an application inside your Amazon VPC, it uses AWS private link to communicate with SageMaker runtime. SageMaker runtime communicates with the SageMaker endpoint. The VPC interface endpoint connects to your Amazon VP directly to the SageMaker API or SageMaker runtime using AWS private link without using an internet gateway, a NAT device, VPN connection, or an AWS Direct Connect connection. The instances in your VPC do not need to connect to the public internet in order to communicate with the SageMaker API or SageMaker runtime. You can also connect to Amazon SageMaker and connect your notebook instances from your Amazon VPC through an interface endpoint in your VPC instead of connecting over the internet. Here's a question. You're using Amazon SageMaker notebooks to clean and train your data. You received a new security requirement that all training data must be stored in a private S3 bucket. What is your solution? One solution is to host the SageMaker notebooks in a private subnet of your Amazon VPC and associate a VPC endpoint for Amazon SageMaker Notebook and Amazon S3. Remember, you can connect directly to the SageMaker API or the SageMaker runtime through an interface endpoint in your VPC instead of connecting over that internet. Could you host SageMaker notebooks in a private subnet of a VPC? Create an outbound network access control list rule that blocks access from the public internet. Well, I added this question because we'll talk about network ACLs under Domain 4, but the answer is no. A network ACL will prevent your SageMaker notebooks from connecting to the SageMaker APIs, which are needed to perform SageMaker operations. So that wraps up task 3.2, and we already covered 3.1. So in the next lesson, we will cover task 3.3 from Domain 3, which is to use automated orchestration tools to set up continuous integration and continuous delivery pipelines.